Hey, welcome back. Let's do this second part of this section 4.4. And let's take a look at all the extreme, increasing, decreasing, critical points, and so on. So we'll run the first and second derivative as well as find our intercepts and other information for this function. So if I have this one, the first thing I would do, instead of expanding that, even though I could, so here's my function. I don't want to take x minus 2, x minus 2, x minus 2, and then multiply by x. So I'm just going to go ahead and when I take the first derivative, I'm just going to use a product formula here. So number one, let's go ahead and take the derivative. Derivative of the first times the second plus the first. Now I'm going to take the derivative of x minus 2 to the third. And then derivative of x minus 2 is just a 1. Okay, so we've got x minus, notice both have, here, let me write it this way. So there's our y prime of x. They both have an x minus 2 squared. Let me take an x minus 2 squared out, and I would be left with one of these x minus 2's from the first one, and then plus that 3x over here from the second term, because I took out both of those x minus 2 squareds, right? Think of it as a cubed plus 3xa squared. I'm taking an a squared out, right? Or x minus 2 squared out. Well, it looks like we got x minus 2 squared, x plus 3x. I got a 4x minus 2. And here's our y prime. So y prime is defined everywhere, so I don't have to worry about the critical point of y prime being undefined. But where is it equal to 0? Well, x equals 2, add 2 divided by 4, so we got a half from that one. And we got 2 from that one. So our y prime test, I'm going to put the 2 on, I'm going to put the 1/2 on. Let's go ahead and test something to the left of a half, like 0. Let me try like a 1, maybe a 3, and we're going to plug it into y prime. So y prime equals x minus 2 squared times 4x minus 2. Throw 0 in, and I got it looks like I got a 4 times a negative 2, so this is a negative. So the original function must be decreasing from negative infinity up to a half. Throw 1 in, and I've got, notice this is always squared. So this is always positive, so it's just a matter of what's going on over here, and this one ends up being positive. So positive times a positive is a positive. So the function is then increasing from 1/2 to 2. And then we'll go ahead and throw in 3. And you've got a positive y prime of 3. This is always positive because it's squared. And then 4 times 3 minus 2 is a positive. So again, positive. So let's go ahead and note that. So we are decreasing from negative infinity up to a half. And then we're increasing from 1/2 to 2, union from 2 on, or you could say 1/2 on. Well, we're decreasing, then we increase, so we go down and then up, so we're going to have a relative min right there at 1/2. 1/2, and then I want to plug it into my original function, x times x minus 2 to the third. So we got a half minus 2 to the third. So we got a half times, what was that, negative 3 over 2 to the third. So I got a half times negative 27 over 8. So I got negative 27 over 16. So negative 27 over 16. Okay. All right, let's go ahead and now take our second derivative and get our information from the second derivative. So there's all our first derivative information that we'll use. And I'm going to go from right here. Here's my first derivative right there. I'm going to use that. So first derivative, now we're going with second derivative. So y, here's my first derivative. I'm going to use the product formula. So the second derivative is derivative of the first. Now it's to the first power derivative of x minus 2 is 1. Derivative of the first times the second plus the first. Derivative of 4x minus 2 is just 4. Notice they both have an x minus 2 and a 2 I can take out. I can take out a 2 and an x minus 2. And I'm left with, over here, it looks like I'm left with a 4x minus 2. And then over here, I'm left with one of these x minus 2s. And I'm left with 2 from that because I took 2 out front. So x minus 2 and 2. In that term, right? Because I factored out 2x minus 2 from both of those. So y double prime equals 2, x minus 2. I got 4x minus 2 plus 2x minus 4. So what's that? 6x negative 2 minus 4 and minus 6. So I could take a 6 out front, combine it with the 2, so I have 12 now, and x minus 1. Again, I factored a 6 out of that 6x minus 1 and combined it with that 2 out front. So here's my y double prime. Let's find our Hilbert numbers by letting that equal to 0. So at x be 2, x being 1, as long as it's defined in the original, and it is. So those are my Hilbert numbers for my y double prime test. So 1 and 2. I'm going to go ahead and test like 0. So I got y double prime as 0. So I got 12, 0 minus 2, 0 minus 1. 12 times negative 2 times negative 1 is a positive 24. So y double prime is positive. So it means it's concave up from negative infinity up until 1. I'm going to throw in like 1.5, so 3 halves, and that would end up being negative. I throw it into the double prime, so it'll be concave down. I'm going to go ahead and plug in like 3, and that'll end up being positive, concave up again. Okay, so let's make a few notes here. I'm concave up from negative infinity up to that 1. And then again from 2 on. I'm concave down between 1 and 2. I do have a point of inflection. That's where it changes concavity. Point of inflection, because it changes from concave up to concave down at 1, and then changes from concave down to concave up at 2. So at both of those, 1 comma whatever and 2 comma whatever. And so I would throw those into my original function, which is x minus 2 cubed. So let's throw the 1 in. So I got 1 times negative 1 cubed. So it looks like I get negative 1 there. Throw the 2 in, and I end up with 0. So those are points of inflection as well. All right, let's start putting some information on the graph finally with all this stuff. So I'm going to start with my relative minimum of 1/2, bless you, 1/2 negative 27/16. So 1/2, halfway to the right. I'm down 1 and almost 2, about right there. Negative 1.7-ish or whatever negative 27/16 is. Okay, so I have a relative min there. This is a relative min, so it's just going to hit that right there. Throwing 0 in would give us a y value of 0. So I could find my zeros from this original. I'm not sure if I did. I don't think I did that yet. Here's my original function. If I let y be 0. I have x being 0 and x being 2 with multiplicity of 3. So it hits at 0, and then it hits at 2, and it's an odd multiplicity. So I know it's got to cross through there. It's got to cross through that. And then finally, if I was to multiply this whole thing out, I'd have x to the 4th plus blah, blah, blah. So it's an even degree, positive leading coefficient. So I know it goes up to the left and up to the right. Now let's incorporate our calculus stuff. I'm concave up until 1, but I'm decreasing. Let's see, I was decreasing till a half. So I'm concave up and I'm until 1, and I'm decreasing to a half. So I hit this relative min right here, but I stay concave up until right there. And at 1, -1, I have that point of inflection. Now I'm going to switch to concave down from 1 to 2. So concave down, 1 to 2. And then I'm going to switch, and I'm still increasing from 1/2 to 2. And then I increase again after 2. And then I switch after 2 to concave up. So I kind of concave up it after that. And again, I could put some more points on. You could obviously punch it into decimals and make it look a little nicer. But it's a pretty decent little graph with all our information there. I'm just going to run a bunch of these, and hopefully you get a bunch of different looks at some that are, with polynomials, as well as some transcendental functions, as well as some exponentials and trig. So let's do this next one. I would go ahead and take this through. So 2/3 plus 6/3 x squared. 2/3 plus 6/3, I got 8/3. And then I would take this derivative. So the derivative, then I can just use the power rule. 8/3 x to the 8/3 minus 3/3 for 5/3 minus 4 times 2/3 is 8/3 x. 2/3 minus 3/3 is a -1/3. So I got, let me write it as this. 8x to the 5/3 over 3 minus 8 over 3. And the third root of x, or x to the 1/3. Let me give both of these an x to the 1/3, x to the 1/3. So we have 8x to the 6/3, which is 8x squared. 3 and the third root of x. And there's our derivative. If you wanted to, you factor in 8 out, and I'd have x squared minus 1 over 3 third root of x. Okay, here's our derivative. And so if you notice, our critical points would be, where's this thing, where's y prime undefined? Well, wherever this third root of x equals 0, if I cube both sides, I get x being 0. Where's y prime equals 0, x being 1, or x being -1 for my numerator. And so my y prime test, so this is number 1, we're trying to get to this y prime test, the first derivative test. -1, 0, and 1. And then I'm going to go ahead and test like maybe -2, maybe -1/2, maybe 1/2, maybe 2 right here. And I'm plugging it in right here, right? So if I throw -2 in, I get 8 times -2 minus 1. So y prime of -2, I got 8, -2 minus 1, -2 plus 1, all over 3 times the third root of -2. So I get 8 times -3 times -1 over 3 times, this is a negative number is the point on this, so I'll have a positive 24 over 3 times a negative number. Well, that's negative. Positive over a negative is a negative. And so your original function is going to be decreasing. Then I would go ahead and plug in -1/2, and that'll end up being positive, so it'll be increasing. Again, I'm putting it into the first derivative. Now I'm going to plug in +1/2, and it'll decrease. It'll be negative. And then I'm going to put in +2, and it'll increase if I put into the first derivative. I'm sorry, so the original function is increasing. So let's go ahead and write, we are increasing from -1 to 0. The original function is increasing from -1 to 0 as well as from 1 on. We're decreasing up to that -1, and then from 0 to 1. We're decreasing, right? So we'd have a relative min at that first -1, right? I decrease, and then I increase, right? I go down, then I go up. So I got to have a relative min right there, as well as over here at 1. Relative min also at 1. And then I'd have a relative max at 0, because I increase and then decrease. Relative max at 0. And I'm plugging these into the original function. X 2/3 times x squared minus 4. X to the 2/3 times x squared minus 4. Well, the 0 is real easy for the relative max. 0 to that is 0. 0 times anything is 0, right? Plug the -1 in. -1 to the 2/3 times -1 squared minus 4. You get the third root of -1 and then square that. And then -1 squares 1 minus 4. So I got third root is -1, -1 squared times -3. So I got -3 on that. So -1, -3. Plug 1 in, and you get -3. Okay. Let me erase that so I don't have that in my way here. Okay, let's move into our second derivative now. So we have our y prime is, let me go back up to right here. I'm going to take it in this form, because then I could just run the power rule. So 8/3, that's my 8/3 x to the 5/3 minus 8/3 x to the -1/3, right? Before I manipulated it algebraically to find my critical point. So I'd take it right there. And so my second derivative would be 8/3, I got 5/3, x to the 5/3 minus 1 is 2/3 minus 8/3 times -1/3 x to the -1/3 minus 1, so -4/3. So I got 40 over 9 x to the 2/3 plus 8/9 x to the -4/3. So I got 40 x to the 2/3 all over 9 plus 8 over 9 x to the 4/3. Let me give this a x to the 4/3, x to the 4/3. And so I've got 40 x to the 6/3, or 2, plus 8, all over 9 x to the 4/3. That's my y double prime here. And so my Hilbert numbers, where's y double prime equals 0 would be if this numerator equals 0. So x squared would be -8 over 40. Well, that's -1/5. And when I square root, we're not working in the imaginary numbers. So that has no solution there, right? That's a complex or imaginary number there. Whereas y double prime undefined, my other potential Hilbert number, well, wherever this 9x to the 4/3, if that's 0, we have an issue. Well, that would be divide by 9, take both sides to the 3/4. So x would just be 0 would be my y double prime Hergert number to test. And now I'm going to plug in like -1 into my y double prime right here. Okay. And so I've got, let me come over here, y double prime of -1. I got 40 times -1 squared plus 8 over 9, -1 to the 4/3. So that's -1 to the 1/3. So the third root of -1 to the 4th. So I got 40 times 1 is 40 plus 8, 48 over 9. -1 to the 1/3. Third root of -1 is -1, but it's to the 4th. So that's positive. That's a positive over a positive. So we are concave up at -1. Go ahead and plug in 1, and you're going to get a positive as well. Concave up, if you can see that. Similarly. Okay. And so let's state where we're concave up from -infinity up to 0, and then from 0 on, or -infinity, +infinity, we're actually concave up, right? Or, I'm sorry, leave it at that. Concave up, -infinity is 0. Notice that 0, I don't think 0 was, 0 is defined in the original. Okay. But 0 is not defined in the derivative, right? So you have some sort of like a sharp point there, right, at 0. All right, let's put it all together, as well as let's find, or let's use our relative min, -1, -3. -1, -3 is your relative min. The other one was a 1, -3 was also a relative min. Relative max was 0, 0. And remember, it's concave up. So it's concave up to there, and then concave again, type of deal, right? But let me see what's going on with the increasing, decreasing here. Let's see, we're decreasing to -1, but we're concave. Yeah, so that's a pretty decent. You know, the other thing I did not find, I should have found my zeros on the original. What were my zeros of this? For the original function, x to the 2/3, x squared minus 4. So I have x being 2, x being -2, and x being 0. So let me put the 2 and the -2 because I hit those points. All right, let's keep it concave up, and we're decreasing to the -1. We're still concave up to 0. Now the derivative is undefined right there, but I do know it stays concave up, but then it decreases to 1. But I stay concave up, and I stay concave up. So that's a pretty decent sketch of that graph. All right, let's take a look at another transcendental here. We've got, or a transcendental, I should say, where we've got a trig function, y equals x plus cosine x. And we want this, though, we only want to draw a sketch of this we're only concerned on this 0 to 2 pi. So we're going to cut this off, right? Because y equals x is all reals, cosine x all reals. We don't care about the whole graph. We just want to look at between 0 and 2 pi. Okay, so let's go ahead and run the first derivative, number 1. Let's go ahead and find the derivative. Derivative of x is 1. Derivative of the cosine is negative sine. So 1 minus sine. Where is it undefined? Nowhere, but where is the derivative equals 0 to find our critical number? Add sine to both sides. The sine of what is 1? And you say sine of pi halves is 1 on our unit circle, right? Now, I know that the sine of 5 pi halves is 2, right? But these are outside our domain. So we're only going to look at this for pi halves. And remember, we're cutting it off between 0 and 2 pi, right? We're cutting this thing off. So let's go ahead and test something in here, like maybe pi fourths, and punch it in to the first derivative. So we got y prime of pi fourths equals 1 minus the sine of pi fourths, which is 1 minus root 2 over 2. So I got 2 over 2 minus root 2 over 2 is 2 minus root 2 all over 2. Well, 2 minus root 2 is a positive number. All right, root 2 is like 1 point something, I don't know. So positive, the original function increases up to pi halves. Then I'd punch in like, I don't know, 3 pi fourths. So we got y prime equals 1 minus the sine of 3 pi fourths. And guess what? We get another positive here. Sine 3 pi fourths is also root 2 over 2. So we got this thing increasing and then increasing. So we're increasing 0 to pi halves and then pi halves on. In other words, 0 up to 2 pi we're increasing. That whole thing, right? 0 tapers off, but then it keeps increasing on up to 2 pi. Okay. And again, we're only cutting it off because the original was cut off there. So we're not worried about the rest. Let's go on to the second derivative. So number 2 here, let me get this out of the way. All right, second derivative. Derivative 1 is 0 minus derivative sign is cosine. So y double prime is negative cosine. Well, where's this undefined? It's not. Where is the Hilbert number where the double primes equals 0? Divide both sides by negative 1. Cosine of what is 0? And you guys say cosine of pi halves is 0. And we also know the cosine of 3 pi halves, cosine of 270 degrees, is also 0. Remember, we're only looking for cutoff between 0 and 2 pi. Don't forget that, right? So we could go ahead and throw in maybe pi halves or pi fourths, sorry, pi fourths. So we got y double prime equals negative cosine of x, pi fourths. Well, that's negative. And the cosine of pi fourths is root 2 over 2. So that's negative, so it's going to be concave down. You punch in, maybe 0. And we got y double prime is negative cosine of, I'm sorry, I can't throw in 0. What am I doing? Throw in like pi. And we got negative cosine pi is negative 1. So we got 1. So we're positive. So it's concave up between there. Something after 3 pi halves, like maybe 7 pi fourths. Throw in 7 pi fourths. You'll get that to be concave down. It'll be negative on that. Okay. So we do have some inflection points. So, well, let's note our concave down from 0 to pi halves, and then from 3 pi halves to 2 pi. We're concave up from pi halves to 3 pi halves. And so we do have points of inflection because they change concavity. Point of inflection at the pi halves. And we have a point of inflection at the 3 pi halves. And so I would want to punch that into my y equals x plus cosine x. Here's my original function. So y equals pi halves plus the cosine of pi halves. Well, the cosine of pi halves is 0, so this just ends up being pi halves. And then punch in 3 pi halves plus cosine of 3 pi halves. And then you get 3 pi halves for that other one right there. Okay. All right, and then if you want to find your zeros, you could let 0 equal x plus cosine x, and you're like, it's not solvable algebraically, or that's going to be a mess to try and find that, and that's because it doesn't hit there. There is no place where cosine of x would be equal to negative x. So if we're trying to, here, let me just sketch this freehand. Graphing. And let's see, we had our increasing from 0 to pi halves, and then pi halves to 2 pi, and then we have, see, we start off concave down. It'd be nice if I threw some points in. Let me throw in like 0 into the original function. Get me started here. I got 0 plus a cosine of 0. That's 0 plus 1, so I've got 1. 0, 1. That would be, at least I can get me started here. And of course it'd be nice to throw in some other points too, but we do have the point pi halves. So that would be 1.57, so it's about right there. And then 3 pi halves, so 4.71. 3 pi halves. Anyways, up here, so we're concave down to pi halves, concave down, and we're increasing, and we continue to increase, but we got to switch concavity, so up, so we kind of go up, and then we have a point of inflection at 3 pi halves, so this stays concave up, but then we have a point of inflection, and we'll switch to concave down until we finish. And that's kind of a decent graph of that, at least with a few points. All right, let's do another transcendental here with the natural log. So we got the natural log 5 minus x squared. Derivative of the natural log of x is just 1 over that. Don't forget chain rule. Derivative of 5 minus x squared is just the negative 2x. So my y prime equals negative 2x over 5 minus x squared. And so, where are my critical points? Well, where's this undefined? Wherever 5 minus x squared equals 0, wherever x squared equals 5, or plus or minus root 5. Okay, where's y prime equals 0? Wherever the numerator, negative 2x, equals 0. So x being 0. I also want you to think about the domain on this one. If you remember just the old natural log of x, looks like this, right? And its domain, there's a vertical asymptote, x equals 0, so x is positive as your domain on that. Okay. Well, this is the natural log of 5 minus x squared. So that 5 minus x squared has to be greater than 0. It's not natural log of x, it's natural log of 5 minus x squared. So let me erase this. So if your note domain is helpful here, because 5 minus x squared has got to be greater than 0. If I add x squared to both sides, I have 5. Let me flip that around. So I have x squared less than 5. Now I'm going to square root. I'm going to be technical about this because I have an inequality here. The square root of x squared is the absolute value of x, right? Is less than the square root of 5, which means I got to be between root 5 and negative root 5 to be true. This is my domain. So I can't be root 5 or root 5. I brought that up because you notice right here, y prime is undefined there. Well, the original function is undefined there anyways, right? I got to be less than root 5 and greater than negative root 5. So that's my cutoff. So I'm not going to even test it outside of those. I just got to test, oops, that's root. Sorry about that. I got to just test something between them and not worry about outside my domain at all, right? So let's throw in negative 1, maybe 1, and I'm throwing it in. Let's do the negative 1 into the derivative. Oops, that's a negative 1. So we got 2 over 5 minus 1. Looks like this is positive. So the original function increases up to 0. Now I would throw in 1, and you'll get that to decrease. Throw in 1 into the derivative. And let's go ahead and summarize this. So we are increasing from negative root 5 up to 0. And then we're decreasing from 0 to root 5. Okay. So we would have, since we're increasing then decreasing, we got to have a relative max there at 0. And so let's go ahead and plug that into our original function, natural log of 5 minus x squared. Let's throw that 0 in for x. 5 minus 0 squared. So we got the natural log of 5 right there. Or that's about 1.6. So 0, 1.6 would be our relative max. So again, some useful information from our first derivative test right there. Let's go number 2. So we have, here's our y prime. I got negative 2x over 5 minus x squared. Let's take our quotient rule then. So the second derivative would be derivative of the top times the bottom minus the top. Derivative of the bottom is negative 2x all over bottom squared. And so we got negative 10 plus 2x squared minus 4x squared. And so we got negative 2x squared minus 10. Let me take a negative 2 out. And there's our double prime right there. And so where's our Hilbert numbers? Well, where's y double prime equals 0? This x squared plus 5 equals 0. Subtract 5, subtract 5. Oh, that's an imaginary number. That's not going to happen. Whereas y double prime undefined, wherever this denominator, square root, add x squared to both sides, square root. So we got plus or minus root 5. Again, those are our edges of our domain anyways. Right? It was negative root 5 to root 5. So we were never going to test outside of those anyways, right? It was outside our domain. So we just got to test something inside like 0. Y double prime is 0. So I'd have negative 2, 0 squared plus 5 over 5 minus 0 squared. So negative 2 times 5, I got a what? Negative 10 over 5 squared, 25. So I got a negative. So this will be concave down throughout its domain. Concave down throughout its domain. No points of inflection, of course. Let's start putting some points on there. So we have 0, 1.6. That was our relative max. About right there. That was a relative max. We're increasing up to 0 and then 0 after. And by the way, root 5 is like 2 point something. So just keep that in mind. And let's see, what else? Let's find where our zeros are at as well for a couple more points. Y equals ln 5 minus x squared. Well, I know the natural log of 1 is 0. So if I can get that to be 1, where does this equal 1? Because I know the natural log of 1 is 0. Let me add x. Let me subtract 1. I got 4 equaling x squared. So x equals plus or minus 2. So I'm going to hit at 2 and negative 2. So if I plug 2 into the original, I get natural log of 5 minus 2 squared, natural log of 1. Natural log of 1 is 0, right? So to hit those two, I'm concave throughout. My domain cuts me off between negative root 5 and root 5. And so this is, and I'm increasing up to 0, and then I'm decreasing after 0, and that's That's about as good as I can draw that thing, for me, at least. All right, let's move on. This next one. I'm going to go ahead and write this as negative 64x squared minus 64 to the negative 1. So when I can just use the power rule. So I have negative 64 times negative 1, 64 x squared minus 64. Now it's to the negative 2, chain rule times 2x. And so I've got 128x over x squared minus 64 squared. Okay. And so where would y prime be 0? X being 0. Whereas y prime undefined? X squared minus 64 equals 0. X squared equals 64. So x equals plus or minus 8. I would make a little note on this. Here's your original function. Let me factor it. See how it's got vertical asymptotes it's at x equals 8 and x equals negative 8? That can be helpful, right? This is a rational function. I'm undefined at 8 and negative 8. But we're still going to test around them. So our critical points here are 0. I know it's undefined, so it's not officially a critical point at 8 or negative 8 because it's undefined in the original. So the only official critical point here is actually 8. But again, I'm going to test around them still. It's very helpful to test around them. So let me plug in like negative 9. So y prime of negative 9, I got 128 times negative 9 over negative 9 squared minus 64. Well, everything's squared on the bottom, so it's always positive on the bottom. And the top here is negative. So it looks like I got a negative over positive, which is a negative. So the original function decreases to there. And then I'll throw in like negative 1. It'll decrease again. And then I'll throw in positive 1. It'll increase into my first derivative. I'll put in positive 9. It'll increase. Okay. And so I'll have a relative min at 0. Plug it into the original. So I have negative 64 over 0 squared minus 64. Negative 64 over negative 64 looks like I got 1. So I have a relative min at 0, 1. I do not have any relative max. Let's go on to number 2. So I have y prime equals 128x over x squared minus 64 squared. There's my first derivative. Okay. Let's take the second derivative. Quotient rule, derivative of the top times the bottom minus the top. Derivative of the bottom is 2x squared minus 64 to the first times chain rule 2x all over bottom squared. So x squared minus 64 to the fourth. So we got, let's see, 128 squared minus 64 squared minus, you know what I'm going to do? Let me take out, let me write it this way. 128 times 2 times 2. Hold on, that would be 4x squared and x squared minus 64. So I'm going to take 128 out of each term there, and an x squared minus 64 out of each term there. And I'd be left with x squared minus 64 minus 4x squared. And I took out that x squared minus 64. And this is all over. So I got negative 3x squared minus 64. X squared minus 64 to the fourth. Well, one of those would cancel, and so I have x squared minus 64 to the third on the bottom. Right now I'm to the third. And so I've got y double prime being, let me take a negative out, negative 128, and make that a positive 3x squared plus a 64. All right, what are my Hilbert numbers? Where's y prime undefined? Wherever this x squared minus 64 to the third would be 0. Can't have the denominator be 0. Take a third root of both sides. Then add 64 to both sides. Square root, x is plus or minus 8. Remember, 8 x equaling 8 and x equaling negative 8 were where the vertical asymptotes were. Where's my other Hilbert number? Where is y double prime 0? Wherever this 3x squared plus 64 equals 0. And so 3x squared equals negative 64 divided by 3. Once I square root, there's none that comes from that. No solution there, no solution, so no Hilbert number from that. So I'm just thinking about y double prime 8, negative 8. Again, recognize 8 and negative 8 were not defined in the original function, but I still want to look around them. So yeah, I know they're not official Hilbert numbers, but I'm going to look around them. So let's go ahead and test negative 9 into y double prime. So y double prime on negative 9, I got negative 128. 3 times negative 9 squared plus 64 over negative 9 squared minus 64 to the third. Oops, to the third there. And so, let's see, the numerator would be a negative. A negative on the top, I got 81 minus 64. That's a positive number to the third. So negative over positive, I got a negative. So we're concave down. Throw in something between them like 0. You'll get concave up on that. Throw in 9, and you'll get concave down again. Right there, into the double prime. Okay? So let's see if we can't throw it together. I had 1, 2, 3, 4, 5, 6, 7, 8. X equaling 8 was a vertical asymptote. X equaling negative 8 was my other vertical asymptote. I had a relative min at 0, 1. Relative min at 0, 1. I was concave up between negative 8 and 8. It'd be nice to throw in some other points, but you're concave up on that. And by the way, I do have this is x to the 0. This is an x squared on the bottom. So I do have a horizontal asymptote of y equals 0. Or you can think about taking the limit as x goes to infinity of that to find the horizontal asymptote too. If you remember that, limit as x goes to infinity of the original function. You divide everybody by x squared and then run it to infinity. And see how you'd have 0 over 1 minus 0. So y equals 0 would be your horizontal asymptote here as well. And then to the left of negative 8, I'm concave down. And then I was decreasing to negative 8 and then decreasing to 0. So decreasing, let me see what I draw this. Decreasing, and I'd plug a couple points in, it would be nice, right? But I'm concave down, and then I'm concave down, but I'm increasing over here. Concave down, but I am increasing from 0 to 8, as well as increasing from 8 on. And that's a pretty decent graph of that without plotting a few more points. Can we sketch it from just the information given? So notice here's like zeros, here's some zeros, and then here's your y-intercept right here. Let's go ahead and put those points on. F of negative 2 equals 0. F of 2 equals 0. So those two zeros are x-intercepts. and f of 0 equals 4. Okay, so here's some points. And then it says f prime of 2 equals f prime of 0 equals f prime of 2 equals 0. So they're giving us the critical points. And then notice they actually give the table as well. It decreases, then the function increases, then it decreases, then it increases. Okay, we've got some more information. And then it says f prime, this one right here, f prime, double prime, sorry. So here's the second derivative, f double prime of -1 equals 0, and f double prime of 1 equals 0. And so I should have, that should not, yeah. F double prime -1 and f double prime of 1 equals 0. So then the sign changed down below for f double prime. So I know it's concave up, concave down, and then I know it's concave up. And so let's see if we could put that together. So we are concave up. Let's see, does it give us any other information there? I guess it does not. We're decreasing to -2, but I got to stay concave up. Decreasing to -2, I stay concave up. Stay concave up until -1, but then I got to switch to concave down. But I got to hit here, stay concave down to 1, and then I'll go concave up again after 1. So that could be some sort of graph with a limited information that we have. That's a pretty decent graph for that. Well, thanks so much for watching. See you next time.